All right, so now what I'd like to do is shift. Instead of gas turbine for power production, talk about gas turbines for propulsion systems. Most of you have flown on an aircraft. Most of you have sat there, looked out, saw the wing, and attached to the wing is what we would call a jet engine. True? In that jet engine, what are you going to intake? Air. And what's going to happen to the air first? It's going to go through a compressor, just like the air in a stationary gas turbine. Then it goes through a combustor. Now it's really hot, and it goes to a turbine, and then it's exhausted. So those are the major components on a simple gas turbine jet engine. There's a number of different designs. You could have turboprop, you could have turbofan, you could have these, but this is just for introductory purposes. That's a jet engine. So if I had time, but I don't, I would take you out and show some videos. I really think these videos are very helpful. Please go look at some videos online. This is a good one on aircraft jet engines, and it talks about different types. What is the main purpose of a jet engine? What does it generate? What does it produce? And I'll ask that question. I'll say, does it produce internal energy? Does it produce momentum, kinetic energy, thrust, or energy? And the best answer is thrust. Then once I get students to say, it's thrust that a jet engine produces, I'll ask, what are the SI units for thrust? Yeah, it's not so easy, is it? So thrust is, and this is where I wish I was using clickers, but I'm not, because I know a few of you know it. But everybody in this room is an aspiring mechanical engineer. Should every aspiring mechanical engineer know it? Yeah. And they should know it like the back of their hand. All right, so what is thrust? Isn't it force? It's a force. And so there's a couple ways of doing force. I know that when I teach fluids, or when I took fluids, is very confusing. So you have a system, and you have air going through the system. And if you focus on the air, it came in with a little linear momentum, and it went out with a whole lot more linear momentum. The linear momentum flow rate went up tremendously, huge. And the only way that happens is there's an effective force pushing on it in the direction of increasing linear momentum flow rate. But whatever is pushing on the gas is probably something like the metal of the engine, and the gas is pushing back on the metal of the engine. Kind of equal and opposite. If I push on you, you push on me. And then you think about the wing of the aircraft. The wing of the aircraft is sitting there like this, attached to it's an engine. It feels a forward thrust to move it down. That's what the wing feels. But what does the engine that's strapped to the bottom of the wing? It feels the force that's opposite, equal and opposite. So you can focus on the wing, or what's attached to the bottom of the wing, or you can focus on the gas flowing through the device, or the device itself. It's a bunch of equals and opposites. But if this is the direction that you're going to be propelling it, the forward thrust is in that direction. It's going to make it move forward down the runway. And it's going to be measured in units of Newton, kilonewton, something like that. Next question. What is a very, very common misconception on jet engines? Would somebody say, the thrust is created by high exhaust pressure? So this is the exhaust part right here, and this is the intake part. And if I took a look at the pressure at the exhaust, compare that to the pressure of the intake, the pressure of the intake is much less. The pressure at the exhaust is much higher, hence I get good thrust. Or is the common misconception that thrust is created by high exhaust temperature? I need the exhaust to be hot. If I just have a hot spewing gas, that's it. Then I'll have great thrust. Or thrust is created by high exhaust speed. What I really want is I want high exit speed compared to the inlet speed. So what is one of these is really wrong. Which one is really, really wrong? The temperature is wrong. All right. Which is the second really, really wrong? A. It's wrong. And this is temptingly wrong. Because it's like this. If somebody says, well, how do I know what the pressure is? I'll do this. Conceptually, I'll put my hand kind of in the exhaust stream. I know I'm not going to do it, but conceptually. And then I'll feel the pressure there. Well, it's going to push my hand out of the way. Wow, that has a lot of high pressure. I put my hand there and got it blown away. But it's not. That's not the case, is it? What it is if you put your hand there, it's a blockage. And that flow that would normally go straight through that area without the hand has to come to rest and then turn and go around. And there's probably a stagnation point right there. And so the pressure built up right there, didn't it? By putting your hand there. It's like if I stick my hand out the window driving down the road of a car, I'll feel the pressure. But what I'm feeling is the hand is forcing the air to come to rest and then navigate to come around it. That's what you're feeling, sensing. But take your hand out and say, you know, did the pressure go up because whatever, it's flowing around my car? No, the pressure right here at the exhaust, guess what? It's equal to the intake pressure. That's what it is. But it's a common misconception. People say, oh, no, it's the high pressure at the exhaust. That's what makes it, you know, go forward. That's what gives it the thrust. No, it's the high exit velocity. So what is our fundamental equation from dynamics, don't shout it out, to predict thrust of a device like a jet engine? Somebody says, I want you to calculate the thrust. Oh, I think we need to take this term and square it and multiply by this and divide it and blah, blah, blah. So what is the equation from really fluid mechanics? I know some people may be taking fluid mechanics concurrently with this class. But if you've already passed fluid mechanics, what is that equation for the forward thrust? All right, somebody's working on it. How about somebody else? Who else? Who knows it? All right, how many people think that a mechanical engineer should know it? Yeah, I know this is always embarrassing, isn't it? Who can help me here? Somebody. Right there. The mass flow rate times the speed. You're absolutely correct, except for one little tweak. And I would accept that. I would accept it as absolutely correct. But there's something about the exit speed, because we also have a inlet speed. And so basically the device has to take something in at certain speed, but really kick it out at a higher speed. Now, a lot of times this inlet speed is negligible. If that jet engine sitting on the tarmac is sitting on the runway before it takes off and it's revving it up, it's ready to start pushing that aircraft. As soon as the pilot lets go of the brake, you can feel it jolt. So it's basically taking, the inlet air is essentially stagnant. It's drawing it in from around there, but it's really throwing it out at high speed. But once the pilot has it up and it's cruising at 32,000 feet, it's cruising at so many blah, blah, blah miles per hour, it could be easily cruising at 0.5 Mach or 0.8 Mach. That's actually a good cruising speed, 0.8 Mach on that, which means that the inlet air to that engine is not stagnant anymore. So the same engine in different condition could have that term negligible on the inlet or not negligible on the inlets. But this is the best equation. Do you like that equation? Do the SI units work? Yeah, they're going to work. They're going to work. So this is mass flow rate times the change in the speed. So let's take a look at the major components. Again, we have the compressor. We have the combustor. We have the turbine section. And those really haven't changed. So what comes out of the compressor goes to the combustor, from the combustor over. Why do they sometimes not show it in line? Well, to leave room for the shaft that's going to connect them. And usually the combustors are kind of in a circle around the periphery. And then But what do we have here, especially if you're flying at high speed? The speed of the air coming into the compressor could be too fast. So what I'd like to do is I'd like to introduce a new device that will have the purpose of slowing the speed down, slowing it down, because it could come in at the very front of the engine too fast to just let it go into the compressor. So what engineering device do I put in the... Perfect, it's a diffuser. Isn't the purpose of a diffuser? Have we analyzed diffusers? Yeah, we have. Haven't visited our old friend diffuser in a while, but it's definitely something in chapters 4 and chapter 6, and we emphasized it. And then this, so what they do is they have the inlet to the compressor, they're going to leave state 1, the outlet 2, which is the inlet to the combustor, then state 3, and then outlet is state 4. Well, they didn't want to renumber, so they say, we're going to call this state A. So again, a letter for a state, but it's what the book uses. So it could have high kinetic energy at state A. So the kinetic energy at A could be pretty big. I'm going to say it's non-negligible. Hence, the speed at A is pretty big. But what happens is you slow it down, and now the kinetic energy at 1 is negligible. It's close enough to 0. So we don't have to consider that in our energy balance. But the inlet to the diffuser, we need to. Now, what about over here? If I really want to kick it out at high speed, and we're going to call that state B. This is state B going out. What do you think? What type of device should I put there as a good engineer to make it go out as high a speed as possible to give me the most thrust? A nozzle. It's not, this is easy, right? So it's a nozzle is what we want. Okay. Now, when we analyze this system, one is getting all the states and then knowing what the devices do. But one of the differences is for a jet engine in a propulsion system, is there a massive shaft running over to an electric generator anywhere, like we had in the power plants? Is there any excess mechanical power that we feed somewhere into the system? No, that's trivial. It's trivial. So what does the turbine put out? If the shaft, there is a shaft out of the turbine, but it for mechanical power, but it only puts out enough to run the compressor. So this is the key. It's exactly the same. So if I have 1 kilogram per second going through, then I have so many kilojoules of shaft work out of the turbine. It is exactly the same amount of kilojoules of shaft work going into the compressor. They are exactly the same. That's different. That's new for this analysis. The other thing is you got to think about pressure. Now, we just talked about the pressure at the exit, B, compared to the pressure at the inlet, A. How does the pressure at the B compare to A? Is it greater than, less than, or equal to A? The pressure at B. They're the same pressure. And so you have to know that the exhaust pressure, the way the engine works, it's just spewing out gases, but it's spewing them out at that atmospheric pressure. The same pressure that's the inlet to the turbine. So there you go. Now, let's ask this. What about the pressure at 4? How does that compare to the pressure at B? Well, I have to know a little bit about how a nozzle works. Is the pressure at 4 greater, the same, or less than the pressure at B? It's greater. It's greater. And think about how you analyze the nozzle. Isn't the higher pressure at 4 better for the nozzle? Won't it make the gases come out faster? It will. It will. And we see that in our calculations. So what you want to do is you want to drop the pressure from 3 to 4 only enough to make enough power to run the compressor. And then you leave 4 as high as you can so you can kick it out the end of that nozzle with the highest speed. That conceptually is challenging for most people when they start to analyze this type of problem. Because we talked about the pressure ratio across the compressor, P2 divided by P1. Isn't that the pressure ratio across the compressor? Is that the same as the pressure inverse of the pressure ratio going across the turbine? Is P3 divided by P4, is that the same? The pressure ratio across the turbine, is that the same as the pressure ratio across the compressor?
No, otherwise you wouldn't have any more pressure to make the nozzle effective.
That's right. You want the high pressure at 4. You want to minimize this. So often it's as low as possible and as distinctly different from the pressure ratio in the compressor. So I may have a 8 pressure ratio in the compressor and maybe a 4 pressure ratio in the turbine. I just need it high enough to make the compressor run. All right. Now the other thing what I want to do is I want to sketch the states on a TS diagram to help us. So let's do this. Move to a clean illustration. These are the same components. Diffuser, compressor, combustor, turbine, nozzle. Right here I emphasize that you could have the compressor isentropic and the turbine isentropic efficiency. So let's assume that they are not isentropically perfect, with 100% isentropic efficiency. But the diffuser and the nozzle are less so. Let's not confuse it too much. Let's let them be isentropically perfect. All right. So now on a temperature entropy diagram, I need to try and make this big. Temperature entropy diagram. I want to first sketch lines of constant pressure. And the lowest pressure will be the PA equal PB. That will be my low pressure, right? What's going to be my high pressure? P2 is equal to P3 is equal to P high. True? So right away I want lines of constant pressure for an ideal gas on a temperature entropy diagram. What do they look like? That's exactly it. They kind of go like this. It did the high pressure like that. They have a little belly to them, but they're pretty much straight lines sloping up. Okay? So where is state A, which is coming in to the system? Somewhere on the low temperature, low pressure line. We'll call that state A. Now, where is state 1 after the diffuser? Straight up. Because isentropic. No entropy generation. But how far up? Not that much is a very good answer. Not that much. So we introduce another line. But you know what? That's a different pressure line. This is the pressure at 1. And the pressure at 1 at the inlet to the compressor is not the same as the pressure at A. The diffuser slowed it down and built up a little pressure. That's what diffusers do. So this is 1 right there. Now, if I have the isentropic efficiency of the compressor and I have the pressure ratio of the compressor specified, the pressure ratio is going to be P2 divided by P1, or is it going to be P2 divided by PA? The pressure ratio for the compressor is P2 over P1 because 1 is the inlet to the compressor. Don't put PA there, okay? All right, now, let's say it's 8 or 9 or 10 to 1, and then boom, you're going to go up, but you're going to do this in 2 steps. You're going to go straight up to state 2S, and then because of the isentropic efficiency, you're going to then calculate 2 actual, the temperature at 2 actual, which has the same pressure. And wouldn't that state be over here a little bit? Wouldn't the actual 2 be right there? Yeah, we've done that before, haven't we? Now, typically in the problem, they say it comes out of the combustor at this high temperature They usually have to specify that, metallurgical considerations. So they put it out here in their state 3. Isn't it at the same pressure as 2? Sure. But now what you're going to do is you're going to expand it. This is where the students may want to expand it all the way down. No, don't expand it all the way down. You expand it down to some intermediate pressure, and this will be the pressure at 4. Usually that pressure at 4 is not equal to pressure at 1. It'd be almost a miracle if it was. It's not. It's higher than the pressure at 1. And you would expand it from 3 to state 4s. But if it's some irreversibility in the turbine, you have some isentropic efficiency of the turbine. Where is 4 actual? Right there. There's 4 actual. Now I'm going to put it from 4 to B in the nozzle. So where is B, state B? Straight down from 4s or from 4? Straight down from 4. Straight down from 4, and that's state B. I think if you can get the sketch of the major components, if you can get this TS diagram down, then it's pretty trivial. Because all you're going to do is remember our famous equation for an ideal gas undergoing isentropic process with constant specific heats. What equation? We have that the T2 divided by T1 is equal to P2 over P1 to the K minus 1 over K. Remember one of those? That's one of our equations we use a lot with the Brayton analysis, Brayton cycle analysis. You know, you can take this equation and rewrite it. Sometimes it's more convenient to have P2 divided by P1 is equal to T2 divided by T1 to the K divided by K minus 1. First of all, do you like this equation? Thumbs up if you like it. The first equation. I forgot to ask, do you like the first equation, or did I write it down in error? So look okay? How about the second equation? Aren't you so glad you took college algebra? I mean, really? Aren't you glad that you took college? Look at that. Can you see that sometimes knowing the ratio of temperatures helps you get the right pressures? And sometimes the ratio of pressures is known, so you need the temperatures. So you're jumping kind of back and forth. You almost feel like, you know, in a circus, jumping here, jumping there. But this is it. It's not hard now if you have all of this. So you ready to start a problem? Let's see how far we can go. First of all, it'll take us a while just to read the problem, won't it? So let's read it. Air enters a turbojet engine at 26 kilopascal and 220 K. Tell me a little bit about that pressure and a little bit about that temperature. It's a low pressure and a low temperature. This is a turbojet engine flying at around about 10,000 meters. That's the atmospheric. I know that it varies a lot, weather conditions, but there it is. There's an average value. At that 10,000 meter altitude, around 32,000 feet, a lot of engines fly around that altitude. And so there you are. It's about 26 kilopascal and about 220 K. Did you hear about a flight? They lost pressure and then they had to dive recently. It was in the news. Some seal broke, and then it's like, if you lose your pressure in the cabin, how would you be as a passenger? And you need to, you just went from 100 kilopascal to 26 kilopascal. I think the pilot took it in pretty good dive to get down. Anyway, let's continue on. We have inlet velocity of 200 meters per second. That's not negligible. So we'll use that in our thrust calculations. The air mass is 18 kilograms per second. That's the flow rate. Air is first slowed in the diffuser. The pressure ratio across the compressor is 8. Negligible pressure drop through the combustor. The turbine inlet temperature is 700 Kelvin. That's specified. That'll be T3. Isentropic efficiencies are given for the compressor as well as the turbine. The work developed by the turbine equals the compressor work input. Basically, that sentence doesn't need to be included. Basically, that's how it works. It's just emphasizing the fact of how the turbojet engine works. The diffuser and nozzle are isentropic. The operation steady state. Kinetic energy is negligible except at the inlet and the exit of the engine. There, the kinetic energy is appreciable, not negligible. You assume constant specific heats with this value of K and that value of C sub P. And now go ahead and make some calculations. Determine the velocity at the nozzle exit, and then once you know that, you get the thrust developed. Well, basically, you make a sketch like I did on the other page. You make a TS diagram like on the other page. You make a table of properties. Table of properties. So we already have the numbering system. So what are our states? State A to start. 1, 2S, 2 actual. 3, 4S, 4 actual. B. That's it. I know I did that fast, but somebody was helping me. We're interested in the pressure in kilopascal and the temperature in Kelvin, and we're given the inlet pressure of 26 and the temperature 220. I'm going to put over here the speed, V, which is in meters per second at 200, and the only place I'm going to calculate is both the A and B. The rest of it's negligible kinetic energy. Can you calculate the kinetic energy in kilojoules per kilogram at state A? How would you calculate the kinetic energy of this condition of the flow at state A? It's 1/2 V squared. All right? So if I put in kinetic energy at A, is it 1/2 200 meters per second squared? What do I get for that? Somebody have a calculator? Can you run it for me? I left my calculator at the office, sorry. Do you have it? Do you have the number for me? Can you tell me the number slowly? No, just give me the number. 20,000. Any more digits? That's it? All right. So do we put 20,000 right over here? What's the error? That's meters squared per second squared. And 1,000 meters squared per second squared is precisely 1 kilojoule per kilogram. And we like to work in energy in kilojoules per kilogram. So it turns out to be 20. How many students on the final exam will put some ridiculous number like 20,000? Too many. Don't do it. Don't do it. All right? All right. Now, what about state 1? I'm going to erase this. This is my working area over here. How about state 1? Well, we have to go through the diffuser. What's happening in the diffuser? We're slowing it down. Do an energy balance on the diffuser. What does the energy balance on the diffuser give you? Inlet enthalpy plus inlet kinetic energy. This is both at A and A is equal to the enthalpy and the kinetic energy at 1, but guess what's negligible? Because you slowed it down. In the diffuser, the purpose is to slow it down, hence you assume that it's negligible kinetic energy at the outlet of the diffuser. And so guess what? This is pretty easy to do. We have that the enthalpy at 1 minus the enthalpy at A is equal to the kinetic energy at A. This is C sub P T1 minus TA equal to kinetic energy at A. The specific constant pressure given, T1 is equal to T2 plus the kinetic energy at A divided by the specific heat, constant pressure. Can somebody run that and tell me we have 220 Kelvin plus 20 kilojoules per kilogram divided by 1.032 kilojoules per kilogram Kelvin. Doesn't it give us all Kelvin? We can add those. So what do we get for T2 or T1? 239.5. All right. Great. How do I get P1? P1. We already used the energy equation. Use the entropy equation. We did the first law, use the second law. But guess what the second law boils down to? Isn't that it? It's like, hey, we just calculated the temperature increase in the diffuser. It's isentropic. Hence, I can get the pressure increase, the pressure outlet. So this pressure, and I hate to retype that equation, but somebody want to run that? It comes in at 35.2 kilopascal. How did we get that again? We just calculated temperature at 1. We know the temperature at A. I want the pressure at 1, and the pressure A is known. And we're given the K value. That makes sense? Where did this equation come from? Second law, isentropic process. That's right. All right. Now, what about the pressure at 2S? It's the 8 is the pressure ratio. 8 is the pressure ratio. So we multiply 35.2 by 8. We get 281.7. It's also the pressure at state 2, 281.7. It's also the pressure at 3, 281.7. Okay. What about the temperature if I have isentropic compression? Is temperature 2S equal to temperature 1 times the pressure ratio 8 K minus 1 over K? So if you go back, we use this equation now, right? All right. And then this temperature comes in at 428.8 Kelvin. But that's if it's isentropic. I have some isentropic efficiency of 80% for the compressor. So it'll be a little higher. And so the temperature 2 actual is temperature 1 plus 1 over the isentropic efficiency of the compressor times temperature 2 isentropic minus 1. I think we've done that a number of times. Go slow here, even though I'm fast. You need to go slow and understand what you're doing, right? And why? But does that look familiar to a few people? Sure, good. So now we have that temperature. It should come in higher, 476.1. It does. We then know the temperature coming out of the combustor that was given to us in the problem statement. That's 700. It's right here, 700 Kelvin. And now we go to the turbine. In the interest of time, I have to stop here. Sorry, wasn't able to finish it. But what's a tricky part about this turbine is you start the calculation saying the work that I need to drive the compressor, I now know. It's the work that I need to get out of the turbine, which is an unknown. And now you work forward. Thank you for your attention.